You hike along a creek for quite a ways. It's a really cool trail. But Yelva, Arkansas, everyone. Okay. Let's get into organic chemistry. So we're going to start with alkanes. But first off, what is organic chemistry? And primarily, we're going to look at molecules composed of carbon and hydrogen. All right. When we say organic chemistry, I don't know if you remember back in 1402, we talked about ionic compounds and covalent compounds. Organic chemistry is more of the ballpark of covalent compounds. Okay. Ionic compounds are like what? You have the cation and the anion. Okay. For example, sodium, cation, chloride, anion. This is not a covalently bonded molecule. This is an ionic compound. Okay, so when we talk about carbon and hydrogen, you'll also see a lot of oxygen, nitrogen, things like that. This is covalently bonded compounds. This is organic chemistry. All right, now why do I have a picture of petroleum jelly? Because how does organic chemistry relate to health sciences? Okay, you guys are all interested in professional health science careers. Okay, whether you want to be a physical therapist or a dietitian or a nurse. Well, petroleum jelly is actually a compound composed of hydrocarbons. So when I say a hydrocarbon, that's a compound that has carbon and hydrogen, a lot of carbon and hydrogen. It may have other atoms as well, but it's dominantly carbon and hydrogen. That's petroleum jelly. Okay, now there are ways we can take petroleum jelly, and you guys are probably familiar with this stuff. It's kind of oily. You can put it on your skin. It's known to kind of be a protective coating or covering for sores or scratches or things like that. We can medicate it. And that's exactly what like Neosporin and Carmex. And there's other things too. We could put prescription drugs in compounds such as petroleum jelly and medicate them. And then you see all sorts of things that are used within the field of health science. Okay. So that's just a cool example that I thought, but digging a little bit more into these atoms. If you need to review, I put these sections on here because these are the particular sections where we, in the textbook, that target covalent bonding and then the geometry, shapes of molecules, the kinds of bonds that these molecules are formed from. So please go review these sections if you feel lost after some of this stuff. But we said carbon, hydrogen, but also you can have oxygen, nitrogen, or halogens. Okay, you guys remember what I mean when I say halogens? What main group is that? Main group, anybody remember?
Is it main group 7?
Main group 7. Okay, that's your chlorine, fluorine, bromine, iodine, right next to the noble gases. So those can be in there. These are the biggest thing though, these are covalently bonded. What do we mean when we say covalently bonded? How is this different than an ionic bond? Anybody remember that? How are the electrons different in a covalent bond than an ionic bond?
They share electrons?
Yes, Madison, okay. So in a covalent bond, electrons are shared. Okay, in an ionic bond, they're completely traded from one atom to another. So you remember the sodium and the chloride that I just wrote up earlier? Na+, this one has lost an electron, completely given it up. Who did it give it up to? Chlorine. That's who's in the compound with it. So here, chlorine is the anode, it gained an electron. Okay, so covalent bonds are different. This is an ionic bond. And we're not focusing on ionic bonds. There will be times when we're talking about organic chemistry, you'll see charges associated with stuff. Okay, so like for example, actually, I'm going to hold off on that for a second. You will see charges, and I'll address those. But we are dealing with shared electrons. So as a refresher, as a reminder, when atoms like carbon, hydrogen, oxygen, nitrogen, when they tend to share electrons, how many do they tend to share? Okay. Anybody remember? This is going to determine how many bonds these atoms will be found to have in a molecule. So carbon, anybody remember how many bonds carbon has to have? Yep. Sorry, I'm trying to, okay, you held up a 4 at the bottom. What's your name? I think you're muted. Sorry. Or you can type it. I want to get to know all your names.
Maggie.
Oh, Maggie. Yes. Thank you, Maggie. 4 bonds. Okay. Maggie, you had a question too that I still haven't answered as far as how we're going to handle lecture on lab.
You did answer it.
I want to say though.
You
sorry.
said we were going to come in.
Do what? Oh, go ahead. What'd you say,
we
Maggie?
would come in.
Yeah, we're still, you have to drive into campus for labs, but if you want to, you're gonna have to come into campus early. So Thursday, for example. Sorry, I just realized I never answered this question. You could do lecture a couple places. I'm still going to do it on Zoom and not in person because I just have all my lecture stuff set up for Zoom. I don't have anything ready for like in-person lecture in a classroom. So I'm going to do it on Zoom, but where can you go to sit? You could go a couple places on campus. You go to the library. If you want to come to room 103 in Mannion Hall, that's where we would typically have lectures. It's what it says on our syllabus and everything. You can sit in 103, just bring your computer, free campus Wi-Fi. So those are a couple places you could come. I'll make sure the room is open and unlocked for you guys, and we'll handle lecture that way, okay? So just make sure you show up, and that way you're already on campus. You take a break, and I'll meet you upstairs for lab 15 minutes later, okay? Okay. All right, back to this. Hydrogen. How many bonds can hydrogen have? Always. Yeah, just one. Okay, we've got one valence electron. You guys should remember how to count valence electrons. Hydrogen can only share one. Okay, oxygen, 2 bonds, but sometimes you'll see oxygen like this, with 1 bond and 3 lone pairs. There will be times you see it like this, and especially on carboxylic acids. We'll get to that in a minute. And it will have a negative charge, okay? Nitrogen should have 3 bonds, usually, but there will be times where you'll see nitrogen like this, 4 bonds, and when that happens, it will have a plus charge, all right? So don't be weirded out by that. There are just times where things in organic chemistry, they bend the rules a little bit. And because you have lone pairs, we know lone pairs can accept a hydrogen or accept a bond. And so you'll see especially oxygen and nitrogen bend the rules that way. All right, now, knowing this, knowing how many bonds everything should form, I'm going to say this. These puzzle pieces, these atoms will come together to form what we call functional groups in predictable ways, okay? And we're about to spend the rest of our time, a lot of our time, looking at functional groups, okay? So these atoms, or what I'm calling puzzle pieces, will combine in predictable ways and patterns called functional groups. Now, what is a functional group? It's just either an atom, or it can be more than one atom. It could be a group of atoms, okay, that has a characteristic physical and chemical behavior. So what that means is when you see certain atoms bonded a certain way, and we recognize that as a functional group, it's going to behave a certain way. It's going to tend to react with either other functional groups or other atoms or other molecules in specific ways, predictable ways. Okay, and that's what we're going to spend a lot of our time the next several weeks learning, is when you see a functional group on a molecule, how is it going to react? What kind of reaction is it going to have with hydrogen? What kind of reaction is it going to have with oxidizing agents or reducing agents? How is it going to tend to behave? All right. They undergo the same reactions in every molecule that contains it. All right. So then we can start to recognize or predict how not just the functional group would behave, but how entire molecules that contain that functional group will behave. Okay. Or how they would be bonded together. Last thing here, the chemistry of an organic molecule is primarily determined by the functional group and not by size. Okay. People tend to think, okay, big molecules can behave a certain way, small molecules behave a certain way. And that's just really far from it. It's all determined by what functional groups are present and then what functional groups it's interacting with. Okay, it all has to do with functional groups. So that leads us to, any questions so far? That leads us to this table. And I know you can't really see this that well, but it is table 12.1 in your textbook. So I would recommend you really, I'm trying to see what page that's on actually. Page, should be pretty early on, maybe not. Should be in one of the first sections, but table 12.1 in your textbook, I would recommend you refer to that table quite a bit. I can't find it, but it's got all these functional groups. So the only one that we're probably not going to talk a ton about is these anhydrides, but everything else you're going to need to be very familiar with. And on an exam, I mean, you're going to need to memorize these. You're going to be able to recognize them on an exam. So we're about to spend a lot of time breaking these down in groups. Okay, so on the next 3 slides, I have a portion of the table broken up. Okay, so we're going to look at the first, I think, 4 groups right here. Okay, hydrocarbons. Okay, so these are functional groups that are just composed of hydrogen and just carbon. No other atoms are in these functional groups. So we call them the hydrocarbon functional groups. All right, so these are families composed only carbon, hydrogen, And they're characterized by carbon-carbon single bonds, double or triple bonds. All right, carbon-carbon single, double, or triple bonds. So you'll notice on this table, the family name, you'll hear me say that a lot. What family is this functional group or is this molecule belong to based on what functional group it has? This is the name you need to know. Alkanes, alkenes, alkynes, and aromatics. So we're going to talk about these one by one. Okay, so alkanes are the simplest of all hydrocarbons. They contain only single bonds. Carbon-hydrogen single bonds, carbon-carbon single bonds. So the example, the way you might see it, this is actually written in condensed, it's a condensed structure. You guys remember writing condensed structures, line structures, regular structure formulas. So if we were to write, this is propane, whoops. If we were to draw out propane, it would look like this. Okay, and then you draw all the hydrogens in, right? So this is propane. We'll learn how to name all these in a little bit. So if you don't know why it's called propane, that's okay. But if you look at this, if you look at Lewis structure, we're going to do that in lab today, draw Lewis structures. You can see it's just carbon-hydrogen single bonds, carbon-carbon single bonds, right? All right. We're also going to learn or familiarize ourselves with what is called line structures. Okay. I'm going to explain this in depth in a little bit, but in a line structures, you just see lines that are connected to as joints. Okay. So anywhere, I'm going to zoom in on this. Anywhere there's a dead end, there's a carbon, or anywhere two lines come together, there's a carbon. Now, what you don't see is all those carbon-hydrogen bonds that I drew out in the Lewis structure. Those are understood here, okay? So if I have a carbon and it's got two lines coming off of it, 1, 2, any lines that I don't see, I know carbon's got to have 4 bonds. Right now, in this line structure, this middle carbon right there, I can only see 2 bonds. So if I know it's supposed to have 4, but I only see 2, what that means in the world of line structures is that I understand the missing 2 bonds are connected to hydrogen. Okay, so there's 2 hydrogens here that I just don't see. That's why line structures are really simple and really nice to look at, because they try to simplify it for clarity, and so they're leaving the carbon-hydrogen bonds, they're omitting those. Anyways, we're going to talk about line structures more, but that's an example. So you see all the examples of the line structures for these. They just give one example for these different families. Oh, and then the last thing to really take note of is the name ending. So if we're going to name this compound, for any alkane, the name ending, it's ANE. So if you read a molecule name and you're not sure what this molecule is or what it looks like, but you see that it ends with ANE, for example, propane, then you know it's just carbon-hydrogen single bonds because it's an alkane. It's in the family of alkanes, okay? So take note, not just of the family name and then what the functional group is, but the name ending. Sometimes that in and of itself will help guide you if you're trying to figure out how to draw a molecule or what family it belongs to. So for alkanes, name ending is ANE. All right, alkenes. The functional group is a single carbon-carbon double bond. Okay, so the atoms that are in red here, that is the functional group. Okay, so double bonds, molecule double bonds, they're an alkene. The example here is ethylene, and you just see in this molecule, we've got that carbon-carbon double bond in the middle. The name ending is ENE. Okay, instead of ANE for alkane, it's ENE for alkenes. All right, I'm going to move on to alkynes. Alkynes, just one step further, we've got a carbon-carbon triple bond. All right. And the example here would be acetylene. Sometimes you'll see with this is another part of organic chemistry that's really hard and sometimes frustrating. There's a systematic naming and then there's a common name. So here you're seeing this is the systematic name, ethine, but also name acetylene. And there will be times where you're going to have to know, okay, the common name is used more often than the actual systematic name. And that can be frustrating and confusing, but that's the nature of organic chemistry. The name ending is YNE. Ine. Okay, you pronounce it as though it's an INE, but it's a YNE. Okay, alkynes. So we got alkanes, alkenes, alkynes. Then the last hydrocarbon family here is our functional group that's in the hydrocarbon family are aromatics. Okay, so what is an aromatic? Notice this looks a little more complicated. These are ring structures. Okay, and it's a ring structure that if you look closely, you'll see these double bonds here, here, and here. Now, what's important about the ring structure is that the double bonds are alternating with single bonds. Okay, so it's not the fact that there's 3 double bonds here. We don't care how many double bonds. What matters and what makes it an aromatic is that the double bonds are alternating with single bonds. Okay, so you have a double bond and then a single bond, and then a double bond and then a single bond, and then a double bond and then a single bond. So you could have an 8-carbon ring structure. Here, this is only 6 carbons. We'll name that a certain way. You could have an 8-carbon ring structure. Let's actually draw that out if I can. Did I do 1, 2, 3, 4, 5, 6, 7, 8? No, I did more than 8. Just want a stop sign, an octagon. 1. I gotta go. Oh, there we go. Now I got it. Okay. If we had an 8-carbon ring structure, you could still make this an aromatic if you have the double bonds alternating with the single bonds. Okay, that would be an aromatic as well. You don't see that often. Mostly you'll see 6-carbon ring structures, but that's an aromatic as well. You could draw a 4-carbon ring structure with alternating double bonds, and that would be an aromatic, right? That would look something like this. That's an aromatic as well, okay? So benzene is the prime example. That's the 6-carbon aromatic that you'll hear us talk about benzene a whole lot. The simple line structure for that is shown in the next column, and we don't have a specific name ending for aromatics, okay? I know that looks confusing because it's E and E, but these are double bonds, okay? Now, so technically, yes, you have the alkene double bonds in there, but we're not going to classify this as an alkene. We're going to classify it as an aromatic because of the way the double bonds are structured within the molecule. Does that make sense? Okay. Any questions on these first 4? All right, carbon bonded to electronegative atoms. So this is the next several, 1, 2, 3, 4, 5, 6, 7, I think here, class of functional groups. So these are different because it's not just carbon and hydrogen anymore. Now we're going to throw in other electronegative. Do y'all remember what I mean when I say electronegative? Y'all heard that word before? What does the word electronegative mean? Anybody remember? It's probably been a minute. Nobody? So if I had a picture of a periodic table, I really wish I did right now. Electronegative elements are those that are close to fluorine. You guys remember where fluorine is? Let me see if I can pull one up really quick. I'm going to share my screen of this periodic table. There we go. Okay, right here. All right, you guys can see this periodic table. So all the atoms, so fluorine is right here. Fluorine's group 7 halogen. Fluorine is the most electronegative element on the entire periodic table. So oxygen, sulfur, chlorine, a lot of these elements in here, the closer you move to fluorine, the more electronegative the element is. Now, what does that mean? I'm still not saying what it means though. If you are electronegative, you like electrons. You attract electrons. You want to gain electrons, okay? Fluorine has 7 valence. If it gets one more electron, it's stable, like a noble gas. It's got 8 in its valence shell. Okay, so because of that, it wants one more electron really, really badly. So that's what electronegativity is. It's the I guess the desire to gain an electron that particular atom or element has. All right. So some atoms want to gain electron more than others, and if you want one really bad, you're what we call electronegative. So when I say electronegative elements, I am meaning elements like. Y'all see my? Okay, what do y'all see my iPad again? No, y'all don't. Share. Okay. Here we go. Okay, so when we say electronegative, atoms such as halogens, here we go, halogens, nitrogen, oxygen, or an oxygen hydrogen group, an OH group, a hydroxyl group. Those are electronegative, all right? So let's look at the very first one. It's called an alkyl halide. The functional group there is a carbon bonded to X, what is X? X could be chlorine, fluorine, bromine, iodine, just the halogens here. Okay, so if you are looking at a molecule and you see within that molecule a carbon bonded to a halogen, that classifies this molecule as an alkyl halide. All right, ethyl chloride is example. We've got chlorine right there. That chlorine is bonded to that carbon. So if we were to draw that out down here, we've got CH3, then we've got CH2, and then we've got this chlorine bonded to that carbon. We got 3 lone pairs on the chlorine. Okay, so this right here, this is the functional group. That's what makes it alkyl halide. If you were looking at it in a line structure format, it would look like this right here. And we don't have a particular name ending, we just call it alkyl halide. And there will be times, guys, where you see a molecule has more than one functional group. And we're going to talk about how to classify those and how to name those as well. Okay, next one, an alcohol. So we got alkyl halide and we have an alcohol. If you see a carbon bonded to an OH group, so not just an oxygen, an OH, there's a hydrogen bonded to that oxygen. We call that an alcohol. Okay, you guys have probably heard of the compounds such as methanol, ethanol, propanol. Okay, these are all alcohols. And as I just said a whole lot, methanol, propanol, ethanol, the name ending here is OL. Okay, so ethyl alcohol, also known as ethanol, is just the example that it gives. All right, so the functional group is the bonding of an OH to the carbon. Okay, next would be an ether. Okay, so there's another one we're going to get to called an ester. Keep esters and ethers separate. Okay, so an ether is an oxygen bonded to 2 carbons. Now we don't know what all, and then it doesn't matter what all these carbons are bonded to. It could be 2 hydrogen, or it could be hydrogens. It could be other carbons. The molecule could extend and be really huge. But when we can zoom in and we see an oxygen bonded between 2 carbons, that is an ether. And it's single bonds here. Okay, that is an ether. So for example, we have a CH3, CH2. If we continue the structure, we see the carbon here is bonded to this oxygen, and then we have another carbon on the other side of that oxygen. So this, because we have that right there, ignore these hydrogens. It's just the way they're written in this structure. But we got this oxygen, carbon, oxygen, carbon bond. That's what makes it an ether. Okay, if you're looking at it in line structure format, it would look just like this. We got the CH3 here, we get the CH2 here, and the oxygen, and then another CH2 and a CH3. Okay. Again, no name ending. That's specific for ethers. You'll often put the word ether at the end of the molecule. That's what you see here, diethyl ether. We just tag that entire name, family name, at the end of the molecule. Okay, so that's alkyl halides, alcohols, and ethers. Now we have several more. Okay, we have an amine functional group, is when you have a nitrogen bonded to a carbon. Okay, now we don't know what's on the other side of this nitrogen. It could be hydrogens, it could be more carbons, but when you can zoom in and see 1 nitrogen bonded to 1 carbon, that is an amine. Okay, an amine. So it gives you an example here of ethylamine. So if we were to draw that out, CH3, CH2, and then we got this nitrogen bonded to the carbon, and on the nitrogen we have 2 hydrogens. Okay, you could have any kind of stuff bonded to the nitrogen though. You could have another CH3 group. Okay, it doesn't matter, as long as you have this nitrogen carbon bond. That's an amine. And then the name ending is the whole word amine. Okay, a thiol. Okay, so that's a carbon bonded to a SH group, not just a sulfur, but an SH group. Okay, so almost like an alcohol, you have an OH group bonded to a carbon, makes it an alcohol. If you have an SH group, then you have a thiol. So those sound a little bit similar. We don't have a particular name ending for thiols the way we do for alcohols. You will just put the word thiol at the end of the molecule. Okay, I'm going to move on a little bit, looking at our time. Disulfides are when you have 2 sulfurs bonded to each other. And then on the other side of that, on each side, you have carbon. So it's a carbon, sulfur, sulfur, carbon bond. Now, this is actually going to be a really important functional group when we get to proteins. Okay, so if you know anything about proteins, there are particular amino acids, especially those of you that want to go into dietetics. Maybe you're familiar with what amino acids we need in our diets and what we don't need, what our body makes. There are particular amino acids that are responsible for making disulfide bonds within proteins, and they help hold the structure of proteins together. Okay, that's a cysteine amino acid. That's besides the point for right now, but that is an important functional group we'll see in the biochemistry section of this course later on. So the example here is dimethyl disulfide. Don't worry about how to name all these molecules yet. We're going to get to that. But in the line structure, again, you see the carbon. This would be a carbon, and then a sulfur, sulfur, and then another carbon. All right. No particular name ending. You just put disulfide at the end of the molecule. Last one is just sulfide. So if a disulfide is 2 sulfurs, guess what? A sulfide is just 1 sulfur bonded in between 2 carbons. Okay. So keep thiols and sulfides separate too. A thiol is when you have a carbon bonded to SH, or a sulfide is a sulfur bonded between 2 carbons. And again, you just put sulfide at the end of the molecule. So this is getting to be a lot. There's a lot of functional groups to know. We've got our hydrocarbons up here that we went over. Now we've got the electronegative atoms involved. We're going to keep going. Any questions so far on any of these functional groups? We're going to do a practice problem in a minute. All right, carbonyls. So we got 2 more, and that's it. Okay, so carbonyls. We do not underestimate carbonyls. You're going to need carbonyls for the next 5 weeks, every single day almost. Okay, aldehydes. Aldehydes are your simplest carbonyls. By the way, I didn't even explain what is a carbonyl. Okay, a carbonyl group is when you have a carbon-oxygen double bond. So if you look at all of these functional groups, you notice carbon-oxygen double bonds. All right, that's what makes it a carbonyl group. But then we have all different kinds of atoms that can be involved on either side that kind of tailor it and customize it into these individual families. So aldehydes. If you have a carbon double bonded to an oxygen, and on the other side of that carbon is a hydrogen, that's as simple as it can get. Notice where are the 4 bonds? 1, 2, 3. So this carbon has 4 bonds. All right. When it's a hydrogen here, that's the simplest. That's an aldehyde. Okay. So if we have I'm going to skip over these examples because we're going to get to naming in a little bit. A line structure in an aldehyde looks like this. Okay. So again, there's the carbon right there. There can be all sorts of things bonded on the other side. But if on one side of that carbon you got a hydrogen, that's an aldehyde. The name ending is Al. Okay, so that's why if we look at the systematic naming for this aldehyde, it's ethanol. Ethanol. Okay, so Al is the name ending for aldehydes. Ketones. Ketone is, instead of a hydrogen on the other side, we now have a carbon on the other side. All right, so I'm not trying to say these are necessarily connected, but so if you have a carbon, and again, that carbon could have all kinds of stuff bonded to it, but if you can recognize this right here in a molecule, that's a ketone. In fact, on both sides, I'm going to erase this, because on both sides, you've got carbon. On either side of that carbon-oxygen double bond, you've got carbon. Okay, so that's a ketone. All right, notice we've got a CH3 here, a CH3 there, so there's our 2 carbons bonded to this middle carbon, and in the middle is where we have the carbon-oxygen double bond. We call this acetone. Acetone is the main ingredient in fingernail polish remover. Okay, so if you've actually ever been around fingernail polish or in a salon, you know what the smell of acetone is. So ketones look like this, and the name ending is O-N-E, but you pronounce it O-W-N, own. Okay, but it's spelled O-N-E, ketones. All right, carboxylic acid. This time, instead of just a hydrogen or a carbon on the other side of that carbon-oxygen double bond, we have an OH group. So we have the carbon-oxygen double bond, and then we have an OH group bonded on the other side of the carbon. I will say, let me go back really quick. I want to make a point. I'm going to erase my scribbles. Aldehydes are always what we call terminal. Notice that they end the molecule, okay? The molecule's done when you see the aldehyde. It can't extend any further. We can't have any other bonds on this side of the hydrogen. Hydrogen can only have one bond. But ketones are internal. Okay, that's one way to differentiate them. Okay, the molecule can keep extending to the left or the right. All right, so that's one way to differentiate aldehydes and ketones. Carboxylic acids, guess what? They're also terminal. I'm not going to write this for every single functional group, but I want you to make that distinction. You can't add any other bonds on the other side of this OH group. Okay, so carboxylic acid, here's an example, acetic acid. So it looks very much like acetone or acetaldehyde, but we just have this OH group. Notice we're just changing that key piece at the very end to get our different functional groups. The name ending is an ic acid, IC, and then the word acid. Okay, so notice for instead of acetone, when it's a ketone, it's acetone, acetone. But when it's a carboxylic acid, it's acetic acid. All right. You could have propanoic acid, oxalic acid, but you always have the ic acid at the end. Okay, anhydrides, again, we're really not going to get into these. These are pretty complicated groups because now we have 2 carbon-oxygen double bonds with an oxygen in the middle. I do want you to be aware that they are a functional group, and there is a section in the textbook that talks about them, but I'm going to kind of jump over these, all right? We're going to move on to esters. So remember, I said there's a group earlier, sounds a whole lot like ester, but it's an ether. So an ether, let's go back and review. What is an ether? An ether is a carbon-oxygen-carbon sequence, okay, single bonds. An ester is when you have a carbon, I don't know who is calling me, sorry. An ester is when you have a carbon-oxygen double bond and then you have an oxygen bonded to that same carbon. The carbon, we call this the carbonyl carbon. When you have 2 oxygens bonded to the carbonyl carbon, but on the other side of this oxygen, you have another carbon. So this is different than a carboxylic acid. Carboxylic acid, you have 2 oxygens bonded to this carbon, but you have an OH, one of them is just a part of an OH group. So an ester is different. It's this whole group right here that makes it an ester, okay? So it kind of has, this portion looks like an ether, but you can't forget the carbon-oxygen double bond, okay? So all together, that's what makes it an ester. I'll be honest, I get esters and ethers mixed up name-wise. Those are 2 of the hardest for me to keep straight. All right, the name ending there is ATE. Okay, so if you're looking at this, we have this whole, we have a methyl group right here. We'll get to that in a minute, but we have methyl acetate. All right. So notice what I want to point out is the ATE ending. And then lastly, well, we got a few more down here. Actually, we already did these. We already did thiols and disulfides. So we are done after this. Amides. Okay, so don't confuse esters and ethers. Don't confuse amines and amides. Amines and amides, they both have nitrogen, but they're different. One contains a carbonyl group, which is the carbon-oxygen double bond. Amines were just a carbon-nitrogen single bond. That's what we looked at up earlier. Amides, you have the carbon-oxygen double bond, and then you have the nitrogen bonded. Notice the different groups on nitrogen. It could be 2 hydrogens, it could be 2 other carbons, or it could be a carbon and a hydrogen. We don't care about that part. They're all amides. Okay, what makes it an amide is this segment right here. The carbon-oxygen double bond, you got the carbonyl carbon, and then bonded to the carbonyl carbon on one side is a nitrogen. These are sometimes hard to recognize within molecules. So we're gonna do some practice. The name ending, you just use the word amide, okay? So we have amines, and then we have amides, we have esters and ethers, and those are all easy to mix up. Okay, questions. This is a lot of information. So we're gonna do a lot of practice. Okay, I see some confused looks. All right, let's put this into practice. So we skip over this slide because we actually already talked about thiols and disulfides. So I have a poll question. I've got 6 compounds here. I'm going to zoom in on them best I can. You should have them on your slides too if you printed it off. I'm going to launch a poll. And if you've never done poll questions, it's anonymous, so I can't see who put what. It's okay if you get it wrong. The sake of this is just for you to practice. I want you to tell me so how are you going to classify the following molecules? So I have number 1, A is best classified as which of the following. I think I actually only did E. No, we did E and F. Okay, there's some that you can only select a single choice, and then there's some you can select multiple choices. So take your time, look at these. We're going to go over them together afterwards. I want to see if you can recognize any of these on your own first. I know this is all brand new, just went over it, so don't feel any pressure to get all of them perfectly right. So let's look at A. I'm going to help get us started. Anybody have an idea on A? What do you notice? So your options for A are alkane, alkene, alkyne, an alkyl halide, a ketone aldehyde, or a thiol. All right. So thiols, if you remember, I just marked it out up here, but thiols have a sulfur somewhere in the molecule. Does anybody see a sulfur in this molecule? So it's not a thiol. Aldehydes and ketones have to have a carbonyl carbon, meaning it has to have a carbon that looks like this somewhere in the molecule. Do we have a carbon-oxygen double bond anywhere in there? Nope. So it's not an aldehyde. It's not a thiol, an aldehyde, or a ketone. So it's one of the top 4. It's either alkane, alkene, alkyne, or an alkyl halide. An alkyl halide has to have a what in it? What does it have to be an alkyl halide?
It has to have an electronegative atom.
It has to have a halogen, a fluorine, chlorine, bromine, or an iodine. And we don't have that. We just have carbons and hydrogens here. So this has got to be either an alkane, an alkene, or an alkyne. So if we go back and look at those groups right here. Here we are. All right. I don't even have an aromatic as a choice, so we're just looking at this top 3. So an alkane contains only carbon-hydrogen single bonds and carbon-carbon single bonds. An alkene contains at least 1 carbon-carbon double bond. An alkyne contains at least 1 carbon-carbon triple bond. So if you're looking at A here, do you think it's an alkane, an alkene, or an alkyne? Okay, so that's A. Put your answer in, what you think. B. Anybody have any thoughts about B?
Is it an alcohol?
Okay, why do you say that, Madison?
Because it has the OH group attached to the carbon.
Right here?
Mhm.
So we got a bunch of carbon hydrogen single bonds. We don't have any double bonds. Okay, so it can't be, I don't even have alkene as a choice, but we don't have any sulfurs, can't be a thiol. We have the OH group. We don't have a carbon-carbon double bond anywhere. So it can't be, or we don't have nitrogen either. If it had a nitrogen, it could be an amine, but we don't have nitrogen. So I like what Madison said, because an alcohol is recognized by a carbon bonded to an OH group. Okay, so that's A and B. You can put your answer choices in there. Can everybody see the poll? Anybody cannot see the poll? I only see 2 answers put in on A.
My poll disappeared when I pressed submit, so I don't know where it went.
Oh, it did?
Yeah.
Oh. Well, maybe you're one of the 2 that have already put answers in.
Yeah, because I can't see it. It went away.
Yeah, maybe you have. Okay. That's all right. If anybody is having trouble with C, does anybody have any thoughts about C?
Would it be the aromatic?
So you're noticing the double bonds here, and we notice that they alternate, double, single, double, single, double, single. And it's all within a ring structure. Okay, so consider that. And what did we say that was from earlier? Okay, what about D? Look at D. Here's what I notice. We have a carbonyl carbon, meaning a carbon double bonded to an oxygen. Okay. Now, what's bonded on either side of those carbons is going to tell us what kind of functional group this is. If we go this way, we've got a carbon. If we go this way, we got another carbon. So which group, think about which group did we say is a carbon-oxygen double bonds in the middle? It's internal. Okay, it's not at the end of the molecule. It's not terminal. It's in the middle of the molecule, so it's internal. And you've got carbons bonded on either side of the carbonyl group. So think about that when you put your answer in for D. Okay. E. I don't know if I made E single or multiple choice. I'm thinking I made it only single choice, but it should be multiple choice. There's actually 2 functional groups here. So I should have made this multiple choice. So if I didn't, I'm sorry. So again, if it helps you to just box them in, I noticed that we have a carbonyl carbon right here. And then we have this nitrogen group on the other side of that carbon. So this right here is a functional group. But then we also have this right here. We have a carbon bonded to a nitrogen. So again, I should have made this multiple choice. There's 2 correct answers because there's 2 functional groups in this molecule. F. What do y'all see on F?
Is there 2 functional groups on F?
There are 2 functional groups. There's one right here, but then we also notice this right here. You see anytime you see a different kind of atom beside carbon and hydrogen, it's probably an idea that there's a functional group tied up somewhere there. So there's 2 functional groups here. So you should be able to select 2 on 6. Yeah, multiple choice. Okay, go ahead and just throw answers in if you haven't. We're going to go through what all the actual answers are. All right, I'm seeing 7, 7, 7, 7. Okay, I'm going to end the poll. I think we're there. If you didn't get them all in, that's okay. All right, so share results. Here's what most everybody said. A is definitely an alkene. All right, all you have is this carbon-carbon double bond. All right, you can't say that it's yes, we have carbon-carbon single bonds and carbon-carbon hydrogen or carbon-hydrogen single bonds. Those are characteristic of alkane, but if you have another functional group, that kind of trumps the alkane family group. So you got to name it with the more complex functional group. Does that make sense? So if you see any sort of single bond or triple bond, you automatically classify the whole molecule as here an alkene because that one one carbon double bond. Exactly what Madison said on B. We got an OH group. So this is an alcohol. Any questions on why this is an alcohol? That's what everybody said. So I think we all agree there. We talked about C. This is an aromatic. because we have the carbon double bonds alternating with carbon single bonds all within a ring structure. Look over here on F. One of the correct answers is also an aromatic. All right, let's look at D. What did we say for D? Okay, we got 2 answers on D, ketone and aldehyde. Okay, I'm gonna erase. Here is what you need to focus. Here's what you need to key in on. Did I just give it away? This is a ketone, okay? Because you have, it's flipped upside down. It looks upside down compared to what it is in the table, if you're looking up at your table. And that's okay. You're gonna find in organic chemistry, things can be pointing left or right or up or down. But there's reasons why they're all the same thing, okay? Because you find there's rotation and twisting that can happen within organic molecules. So this is okay, that's pointing down. That doesn't make it something different. But it's internal, okay? So remember, I'm gonna scroll back up. We said for ketones, if it's internal like this, you got the carbon-carbon single bonds, and then you got the carbon-oxygen double bond in the middle. That is a ketone. It's not an aldehyde because the carbon-carbon double bond does not have a hydrogen directly attached to it, okay? So let's go back down and look. See this carbon right here? There's no hydrogen branching off of this. If we did have a hydrogen there, it would break all the rules for carbon. You can't have 5 bonds on a carbon. You can only have 4. And we reach our 4 with the 2 carbons and the double bond to oxygen. Okay, so any questions on that one? That one is a ketone. All right. Okay, 5, y'all said amide. So this right here, this functional group, this is an amide for sure. You got the carbonyl carbon, that's the carbon double bonded to the oxygen, and then directly branched off that, you have a nitrogen group. So that makes it an amide. Now, if I would have made this double or multiple choice the way I should have, the other correct answer is that this one is an amine because it's a carbon nitrogen single bond. So you got 2 functional groups there. One is the amide, one is the amine. Now, we can't say, we can't say, well, this is an amide. Why is that not an amide? Because you have this carbon in the middle here. This nitrogen is not directly bonded to the carbonyl carbon. To be an amide, you have to be directly bonded to, that nitrogen has to be directly bonded to the carbonyl carbon. Does that make sense? So that's why this one is the amide, and then this one is the amine. Okay, and then lastly, people said disulfide and aromatic. Good. So this one is the aromatic, and this one is the disulfide. Whoops. Okay, does this guys, are y'all a little more comfortable after doing a problem like that? There's gonna be a whole lot of practice problems in the book that we can do. In fact, we have a little bit more right here. So I want you guys to look, this is an amino acid, phenylalanine, and I want you to tell me what functional groups do I have circled here. So this first one on the left, what functional group is that?
Aromatic.
Uh-huh. Okay. We have another functional group. What functional group is this one? The one in the middle with the nitrogen.
Is that an amide or amide?
Okay, so this right here, if you're looking at the line structure, this would be a carbon. And then you have this, the nitrogen directly bonded to the carbon. Don't be confused that this is a wedge looking thing. This is an amine. Yep. All right. Next, we have this last group right here circled. Anybody recognize what this is?
Is that the carbolic acid?
Close, carboxylic acid. Uh-huh. So what we have here is a carbon double bonded to an oxygen, and then we got an OH group branched off of that. So this is a carboxylic acid. Yep. So again, this is just getting you familiar with how to recognize these functional group within molecules. I'm going to let you on your own time look at, this is the structure for Tylenol actually. And so there's a couple of groups within here. There should be 3. And I want to see, you can do those on your own time. If you have any questions about that one, just let me know. But I'm going to move on to, so that's functional groups. So that's the first big topic I wanted to cover. We got about 15 minutes left before we take a break. So we're going to get to isomers and possibly condensed structures. So how do we represent molecules? How do we draw them? And how do we recognize if things are drawn slightly differently? Sometimes you can have the same molecule or related molecules. And that's where you get to isomers, okay? So what is an isomer? It is a compound with the same molecular formula, but different structural formulas. Okay, what does that mean? What is a molecular formula? What's a structural formula? Okay, for example, I want you to consider C4H10. This is the molecular formula. All right. If we draw out C4H10, what you see here, okay, I'm going to draw arrow, these 2 structures below my arrow, these are the structural formulas, like the Lewis structures, okay? Those are the structural formulas. And you can see if you're looking at these 2, both of them have 4 carbons, and if you count all the hydrogens, both of them have 10 hydrogens. But they are arranged slightly differently, okay? So we have 2 different structural formulas, but they have the same molecular formula. Hold on 1 second, sorry guys. My husband walked in for a second.
How much?
5 milliliters. Okay. So going back to this, molecular formula, 2 different structural formulas. This is what we call an isomer. Okay, so these 2, we have the straight chain form. All the carbons are in one straight chain versus we call this a branched chain form. So if one of the carbons is branched off of what we call the main chain, we have straight chain and branched chain with different structural formulas. So we call these isomers. And sometimes it can be hard to recognize these. So I want you to actually draw the possible isomers, all the possible isomers for C2H6O. So we're going to do that. So we have a molecular formula here that has 2 carbons, 6 hydrogens, and an oxygen. So what are the possible ways we could draw this out? There should only be 2 ways we could draw this out. So I'm going to connect my carbons, and I'm just going to start putting hydrogens around it. Okay, so if I do that, I have 2 carbons drawn in. I have 5 hydrogens drawn in, but I still need an oxygen and another hydrogen. I can't put a hydrogen right here because then I don't have a spot for my oxygen. Okay, so I'm going to put my oxygen right here, and then I can put a hydrogen branched off of it right there. So that's one way you could draw this molecule. Did anybody think of another way? Anybody can imagine another way we could draw this? Sometimes it's just trial and error. If we put some people might think, oh, well, we could just put like the OH group down here, right? And then put all the hydrogens. Well, this would actually be the same molecule, okay? So this would not be an isomer. This would be an identical molecule. So it does not matter at which point you branch the OH group off. If the OH group is on the perimeter, it's the same molecule here, okay? You could flip it and turn it. These bonds can rotate. Okay, so we can't do it like that, but what we could do is we could put carbon, oxygen, carbon, put the oxygen in the middle. We still got 2 carbons and oxygen. Now we need 6 hydrogens. 1, 2, 3, 4, 5, 6. Okay, so now we have an entirely different molecule, but it's got all the same number of atoms. So you guys see how this is an isomer? Same molecular formula, but different structural formula. So these would be isomers. Okay, any questions on isomers? We're gonna do more practice problems. I think I have some of this on your homework. Another way we can represent, so also, if you want to practice with isomers, there's a few problems I listed right there. Condensed structure. I know we got 10 minutes left. We've been going for a long time. I'm feeling it too. Hang in here for the last 10 minutes. We're going to take a break. Another way you can represent molecules is what we call the condensed structures. And we've actually already seen examples of this when we were talking about the functional groups. So instead of drawing out every carbon-carbon bond and every carbon-hydrogen bond, like in a Lewis structure, we can condense it, okay? Instead, we can just draw the carbons with their bound atoms. So which ones are directly bound to which carbon? So for example, we have a molecule called butane here. We'll talk about how to name butane, but the structural formula is shown. The Lewis structure essentially is drawn out. So we got 4 carbons in a row, and you got hydrogens branched off all these carbons. Instead of drawing out all the bonds, you could represent this in the condensed formula like this. CH3, so that's this group, CH3. Then this CH2 group right here is just going to be this carbon with the 2 hydrogens branched off of it. Then the next group, CH2, is just going to be that group right there. And then the last one, CH3, is this last CH3 group, okay? So you could draw it like that. And we do this a whole lot, especially for really big molecules. It gets really hard and complicated to draw them out, so we use condensed formulas instead. How would you do it, though, if you have a branched chain? Straight chain is really easy, but the moment you branch something, the condensed formula gets a little more difficult. So you could do it like this. You see you've got these 3 carbons in a row with their bound groups. So this is the CH3 group that you see right here. Next, we have this carbon with the hydrogen branched off of it. So we've drawn that right here. And then the CH3 group up top is just branched. So you can actually draw it branched off. Or sometimes what I wrote below is that parentheses are also used to indicate multiple groups, either in a row or functional groups that are branched. So the way I would accept it as well is if you wrote it like this: CH3, CH, and then in parentheses, CH3, and then another CH3. This CH3 is that one. The one in parentheses is the branched one. The first CH3 corresponds to the first one. Okay, so anything in parentheses can mean that it's branched, and it doesn't matter. If you look, it says you can draw it branched up, or the CH3 could be branched down. It does not matter. It's the same thing. All right. Another way that parentheses are used. So for example, if I wanted to use parentheses to draw a further kind of shorthand notation of the straight chain butane molecule here, we could draw it like this: CH3, and then I could say CH2, 2. I've got 2 of them in a row, and then CH3. Okay, so parentheses are used to indicate multiple identical groups in a row. For example, this straight chain one, you can say this 2 right here just means I've got 2 in a row. Or they can be used to indicate groups that are actually branched up or down. You have to look at your molecule. If you're like, well, how do I know which one it means? You have to look at what makes sense bonding wise, okay? It would not make sense to say that these 2 groups are branched up and down off of that. That carbon would then exceed 4 bonds, okay? So usually if you look at the way it makes sense as a Lewis structure, you can figure out, oh, these are just in a row, groups in a row, identical groups, or one is actually branched up or down, okay? If you've got a subscript on the outside, that usually just means it's identical groups in a straight chain row. Does that make sense? Okay. I'm gonna kind of pause. We're gonna pick up with line structures. We really did not get, what slide did I even get to? Yeah, we only got, wow, halfway through. So we're gonna definitely continue this for the first 45 minutes or so of our lab time. And then we'll work on the Lewis structure lab. But any questions from you guys before we take a break, and we'll come back at 10:45? Anything on the functional groups or condensed structures? We'll practice writing condensed structures on the lab as well. Okay. Well, we'll hop off here and I'll see you guys back at 10:45 on the same Zoom time, okay? All right, y'all take a break.